Okay, so let's continue with the proof. Um, so here is the expression for the mean squared error, where it's 1 over n, the error squared, right? So error is the difference between yi, the output, and the expression for predicting the output that we pass it, I guess. In this case, it's b naught plus b1 xi, but you could have many more terms, right? b2 x2 square or xi square, etc., or you can have multiple inputs. However complicated the right-hand side expression is, as long as b1, b2, b3 are all appearing linearly, um, the matrix version of the mean squared error expression is this. This we've already seen. It's y minus xb transpose y minus xb divided by n. Okay, and this is the expression we want to minimize. We want to find the value of b such that this expression, this number, is as small as possible given values for y and x. Um, because we are trying to minimize this quantity, um, it's the same as minimizing n times mean square error. N is just a constant. Once you know the data, n is just a number of data points. And minimizing a function is the same as minimizing some constant times that function. The value of b at which the function is minimized is going to be the same whether you minimize 5 times the function or 2 times the function or 20 times the function. Okay, the whole function gets lifted up or down. So in any case, that's why we're bringing n to the side and saying let's minimize n times mean square error instead of the mean square error, so that the expression is simpler and we don't have to carry around this 1 over n. Okay, so I just brought these matrices down here, and I've already simplified a little bit. This y minus xb transpose, I brought the transpose inside, so it's y transpose minus xb whole transpose, and xb whole transpose is b transpose x transpose. The order reverses when you take the transpose inside, as we saw on the previous slide. Okay, so that's this thing, and then you have these two matrices that you're multiplying, and you can just multiply that through just normally. Um, Usual rules of multiplication. Okay. Okay, so that's the expression. We want to find b such that this expression is as small as possible. We can simplify this expression a little bit. It turns out this expression and this expression are actually identical, and we can show that in the following manner. So first of all, note that each term in this expression is actually a scalar. It's a real number. This is a real number, this is a real number, this is a real number. Why is that? Because the mean square error is actually a single real number. We just happen to write it in terms of these matrices, but this matrix multiplication reduces to a single real number, right? And then we've expanded this matrix multiplication out, and what we get is a bunch of terms. Each term is basically a single real number, so that you add them to get the mean square error. Okay, so why am I saying it's a scalar real number? Well, if you have a real number and you take the transpose of that real number, of course, the transpose of the real number is the real number itself. The number 5 transpose is basically going to be 5, right? So that's what we're going to do. We're going to take this expression and then take the transpose of it and equate it to it. So if you take this expression, we are saying that it's equal to that same matrix transpose, and then you bring the transpose inside, you get y transpose xb. Okay, it becomes the reverse, and then you take the transpose inside, it becomes this b transpose x transpose y whole transpose is y transpose x transpose transpose, which is x, b transpose transpose, which is b. Okay. And notice that this is basically the same as this. You started with this, ended up with this. So we can plug this in here, and this expression becomes this expression. You get y transpose y minus 2 times this quantity, because these two are the same, and then this just the same as this. Now, we bring 2 outside. and we bring 2 outside and essentially have this divided by 2 because we want to um, have the thing inside the brackets be in the same form as this expression. Okay. So to find b that minimizes L, this expression is what we're calling L. We just need to differentiate this with respect to b. We don't care about this 2, but 2 just goes along for the ride. And we differentiate this expression. Recall that this expression is basically the same as this expression, with c equals this quantity transpose. And x transpose x is basically your Hessian H. Okay, so if we differentiate this, we just use this formula. We say C plus HP. C is basically this quantity transpose, because this is actually C transpose. So that's what comes down here. Derivative of this with respect to B is just 0. Derivative of this with respect to B is H times P in the above expression, where this is H. So we get this. Okay, so this needs to be equal to 0 for B to be optimal. So we just bring this down here, take this to the other side. So we have x transpose xb equals y transpose x whole transpose. And because this is still a scalar, right? So y transpose x is a scalar quantity. Well, actually, it doesn't matter that it's a scalar quantity. In any case, if you take the transpose of this quantity, you get x transpose y, okay? When you bring this inside. Okay, so that's it. We have x transpose xb equals x transpose y, and we go b equals this inverse times x transpose y, as long as this inverse exists. And it turns out that x transpose x is a square matrix, whatever size or shape x is, and it will be invertible as long as the columns of x are independent linearly. And this formula assumes that x has more rows than columns. Okay, in other words, more data points than there are inputs. Okay, just a brief note. We are pre-multiplying this y quantity with this quantity. This quantity is sometimes called the left pseudo-inverse of x, or left Moore-Penrose inverse of x. It's called the left inverse because if you take this quantity, actually this t needs to be up here, seems to have moved around a little bit. But in any case, if you take this matrix and then multiply it by x, where x is on the right side, you get identity. That's why it's called the left pseudo-inverse, right? So because if you multiply this thing on the left side to x, you get identity. There's also something called the right inverse, which is given by this somewhat related expression, and the right inverse satisfies this quantity, x times x inverse, x pseudo inverse equals I. Okay, but of course, for this linear least squares problem, what we care about is the left inverse. We don't really care about the right inverse, at least the way this has been posed. Okay, and I just wanted to briefly note that, of course, all this works if you have more inputs and so on, as we've seen before. And this equation, this formula, is also sometimes called normal equations due to a particular geometric interpretation of this linear regression process. Okay, like I said, this proof was just meant to give a flavor of how some of these things are derived, so that things like this are not unfamiliar when you read a book. It's not super critical to actually solve the homework problems. Although in the homework problems and in future MATLAB programs, we might actually use this expression, but not the proof itself. Okay.